everyone. How's it going? My name is Liz from the Dfinity Foundation, and welcome to Community Conversations. This is an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. So the rapid growth of smart contract canisters and users on the internet computer presents interesting engineering challenges. Recently, there has been an increase in memory-intensive smart contracts, and it's been noted that the memory system has become a performance bottleneck, causing drops of the finalization rate and timeout errors under heavy load. In this community conversation, principal engineer Ulan Dagembayev will show how the team optimized the memory system to fix the performance issues. Feel free to take it away, Ulan.
Thank you, Liz. Can you see my screen, share it?
Yep, I can see it.
All right, yeah, so this talk is about performance in the context of the memory system. And I'll talk about the performance bottlenecks we found, discuss performance issues and open problems. And I know talking about all these problems and bottlenecks, it may sound negative, maybe grumpy, but that's why I want to mention in the beginning that having performance and scalability problems is actually good news for the ecosystem, because this means that the user base is growing, there are more smart contracts running different diverse workloads and uncovering these performance bottlenecks. And we, as a community, just need to stay ahead of the curve, so to ensure that these bottlenecks do not hinder the growth, right? And another thing to mention is that the performance that is perceived by users comes not only from the actual implementation of the internet computer, but there are other factors. For example, the language runtime can have big impact on performance. And of course, there's also the code of the smart contract itself, right? If the smart contract uses suboptimal algorithm, for example, if it needs to scan 1 gigabyte of memory to serve a query, then it doesn't matter how fast we make the language runtime and internet computer, because the performance will be dominated by that suboptimal algorithm in the smart contracts code. And I think this is one area that needs improvement, because we want to welcome and support developers of different skill level, right? From the very beginning, beginners to experts. And one way to help them write performant code is to provide excellent developer tools. And I think this is the area that the community should invest more. And yeah, if there's a takeaway from my talk, I'd like that to be it. And now the main part of the talk will be about performance of the internet computer, because this is the area I work in. So I'll do a deep dive into the memory system and show the bottlenecks and the optimizations we did there. Then I will talk shortly about the Motoko performance and mention the known issues that the Motoko team is working on, and also share some tips for developers. And I will conclude with kind of my wish list of important developer tools that are important for performance and that are currently missing. Okay, so for the main part, we are focusing in the execution layer of internet computer. So this is a layer that's responsible for executing smart contracts, so canisters. And let's walk through one execution. Let's say we have an update message coming from the messaging layer. And to execute that update message, we need to find the corresponding canister, and we need to find the corresponding method in that canister that's responsible for handling the message, and then execute that code of the method in the WebAssembly engine. And these colored boxes within canisters, they represent the state of the memory. And when the message executes, as one of the results is it can modify the memory, right? And one thing that internet computer provides is so-called orthogonal persistence. So this means that all the modifications in the memory coming from update messages, they are automatically persisted and replicated, so that the developer don't have to worry about it. And these modifications are then available to subsequent messages and queries. Now I'm going to kind of look under the hood and show you how orthogonal persistence is implemented currently. And any implementation of orthogonal persistence needs to answer like these two questions. First is, okay, we have the persisted memory of the canister. How are we going to map it to the memory of the WebAssembly engine corresponding to that instance? And then when the WebAssembly is running, how are we going to keep track of modifications in the memory so that they can be persisted later on? And the main constraint here that kind of rules out many implementations already is that we want the whole execution to be very fast, like especially for messages that don't do a lot of work. Like, for example, many queries and messages that touch only a few pages and then execute only few instructions. And for those, we want the execution to be very fast, like sub-millisecond, right? So everything that takes like from instantiating the WebAssembly engine and running the message, it should be fast. Another constraint that increases the complexity of the implementation by a lot is the requirement to support concurrent query execution and execution of the query like against older states. So far we looked into like update messages, right? And they are nice in the sense that they are executed sequentially, but Internet Computer also supports queries, and queries can come at any time, and they are not synchronized with like execution rounds that are replicated. So the queries by themselves, and they are not replicated. And this means that if you take some point in time, there could be actually multiple versions of the same memory, like of the memory of the same canister present, right? Because as execution of the messages, update messages makes progress, there could be some queries that's using older state, or there could be multiple such queries. And if a query is very long running, it could be like using even older state. So the main message of this slide is that the implementation needs to support multiple versions of the canister memory. And the current implementation uses the following approach. For fast instantiation, we rely on page protection and lazy map and map memory lazily. I will walk through this in detail shortly. And for multiple versions, we use a persistent tree data structure. Like the word persistent is like, do not confuse it like with persisting into disk. Like it's just a term in computer science, and it's means that persistent data structures they are usually immutable and support multiple versions. Like a modification of a persistent data structure produces a new version, but older versions are still available. And so, like in summary, it would be that you can easily clone a persistent data structure in a cheap way. So they are quite well known in like functional programming community. Okay, so the implementation of the canister memory consists of two parts. Like the first is the actual file where the memory is stored, and then on top of it there is this persistent tree that keeps track of modifications, and all modifications. Like the time window for the keeping track of modifications is between checkpoints. Like every n execution rounds, where n depends on the subnet. I think currently for most of the application subnets n is set to 500 execution rounds. So there is a checkpoint, and the persistent tree keeps track of modified memory chunks since the last checkpoint, and the granularity of the chunk is operating system page, which is 4 kilobytes. And on checkpoint, all the modifications are committed to the file, and then this file is cloned so that we get the new state for the next rounds after that checkpoint, and then this like repeats. Now, how how are we going to map the pages to the WebAssembly instance and how we keep track of the modifications? Initially, like as I already mentioned, like we use page protection. So initially the whole address range of the WebAssembly memory is marked as not accessible. So it's kind of protected against accesses. And any access, read or write, is going to trigger a signal. And then the signal handler has chance to run and like fetch the memory and keep track of dirty memory. Okay, let's walk through an example. Let's say we have a workload that just accesses the memory from left to right. So the very first access is going to trigger a signal. Then it's the job of the signal handler to fetch the corresponding bytes from the canister memory. In this case, this page comes from the checkpoint file, so that it was not modified since the last checkpoint. In order to like write the bytes, the signal handler needs to change the page protection flags using system calls, right? So it's already doing one system call to make it read write, but then it needs to turn it into read only because it also needs to keep track of write accesses. So after this operation, the page is accessible for reads. So this means like if a canister does reads from the same page many times now, all the reads will be fast. They don't need any intervention from the signal handler. But a write access is going to trigger a signal, and this is where the signal handler has a chance to record, okay, this page was modified and needs to be persisted later on. And if we imagine like this access pattern going over the whole memory, we get like many signals, like there will be as many signals as, or twice as many signals as there were pages, because like assuming the first access was read and the second is write, like we get 16 signals, and then number of called system calls is even more. And this actually turned out to be the bottlenecks that we discovered. Like the system calls themselves are very slow, but if we combine it with the fact that we execute canisters in parallel, so multiple canisters can run in parallel, and all canisters are doing the system calls, and the system calls are handled in the kernel, and kernel has a lock or semaphore for handling such page protection changing system calls. And that was the actual bottleneck, right? So we have, on the one hand, like parallel execution of canisters, but they are all sequentialized in the kernel. And in some cases, so slowdown was like even more than like just running them in sequentially. So it was like real bottleneck we saw in production. And to fix it, we implemented like 3 optimizations that I will describe now. The most impactful one turned out to be the last one, but the first 2 also help a lot. So the first one is based on the observation that if the memory is coming from the checkpoint file, like we can simply map everything that is not overlaid by the modified pages, right? So this mapping can happen like all at once, and it's a copy on write mapping. So this improves situation for the read accesses, because like read accesses can be done like on all this range, on all these ranges without any help from the signal handler. But for the write accesses, we still need to keep track of modified pages, right? So, and that happens on the granularity of a page. So like this optimization helps for reads, but when we do write accesses, we still get a lot of signals like for each page and system calls correspondingly. Now, the next optimization is kind of a low-hanging fruit for queries. So the difference between queries and update messages is that queries do not preserve the state, right? So after execution of a query, we don't have to get modified pages and commit them, like we throw away all the changes. This means that for queries, we can map the portions that come from checkpoint file as read-write accessible. So because we don't have to keep track of the modified pages. And yeah, this helps a lot for queries, but the problem still remains for update messages. And for that, we implemented the following optimization. It's based on the idea that when we get a signal and now need to fetch the page either for read or write access, we can actually look at the pattern that access pattern that happened before that page was accessed and use that as a hint on how many pages will be accessed in the future. So this allows us kind of to, within one signal handler invocation, to prefetch more pages, and those pages like amortized by previously accessed pages. And yeah, and this optimization turned out to be like the most impactful of all three. And when we shipped the version containing all three, like we saw the following improvements. So average execution time improved. So this is a real subnet, and the red line shows the moment when the replica was upgraded to the version with optimizations. And the average execution time improved by a factor of 3. The maximum execution time improved a lot, like 10x improvements there. And yeah, I have also a blog post like describing these optimizations. Now, the question is like, okay, we optimized it, are we done? And the answer is no, because as I mentioned in the beginning, there are other factors, right, affecting performance. And one of them that we see currently in production is the bottleneck coming from the garbage collector of Motoko language. The current version that is shipping is based on the copying garbage collector. It's called Tini's copying garbage collector. It is the right and garbage collector to kind of bootstrap the language. Because, like I know many languages and virtual machines start with this collector, and the main advantage is that it is simple to implement and use. And the main disadvantage is that it is not as performant, and it results in copying a lot of data. So on the high level, it works by splitting the heap or the memory into two halves, and then it copies all the objects surviving from one half to another. So like like as a summary, it touches like a lot of pages and modifies a lot of pages and like stresses our orthogonal persistence implementation. Like Motoko team is busy with improving this. So there's already one improvement implemented by Omar. This is another garbage collector, which is based on the algorithm that marks, like finds all reachable objects and then compacts it. So it decreases number of copies by a lot, but it still copies because it always compacts the heap. It is currently available behind the flag. Like if you compile it, your Motoko canister with the -- compacting GC, it will be enabled, and you'll be using that garbage collector. And I think Motoko team is planning to enable that by default. And in the future, there are more optimizations planned here. So in the future, the plan is for Motoko to get a modern garbage collector, which is based on generational scheme. And also it's incremental and doesn't move a lot of objects. So it will be likely the incremental mark sweep with partial compaction. Now, regarding the tips, so the first tip is like, okay, try out the compacting GC. It should improve the performance. Then another kind of high-level tip is to try to keep your canisters up to date with the latest release, because that's the only way how Motoko team can improve your canister. And as a sneak peek, the next release, like Motoko team is planning a huge improvement in garbage collection scheduling algorithm that will improve performance for like large canisters that consume more than 1 gigabyte. Another tip would be to like if you know that there's going to be a big launch or like maybe some drop of NFT, and you know that there will be a lot of users using your canister, please try to stress test it beforehand, and see how it behaves, with many messages, how it behaves if the memory usage grows to several gigabytes. What is the plan if it hits the 4 gigabyte limit and is going to run out of memory? And when you do such stress tests, you will potentially uncover maybe issues in Motoko or Internet Computer, and then you have a chance to talk with us and we can fix it and ensure that the launch is smooth. And another tip is to avoid deprecated functions. So there are known functions, for example, array.append, that have performance flaws and they are suboptimal. In this example, the append is going to do linear operation, it's going to copy on each append, it's going to copy the array, and it's very suboptimal and also stresses the garbage collector. All right, so that's all from Motoko, and I'd like to conclude this talk with discussion of open problems and the tools that I think we need to invest in, to enable developers to write performant code. So the very first is actually getting metrics from production and from canister, right? Because if we cannot measure it, we cannot improve it. Or the same applies to developers. If developers cannot measure it, they cannot improve it. And for that, it would be great to see some kind of solution that works not only for Motoko, but for all canisters implemented in different languages. And I think the main thing that's needed first is get some aggregated data about how much time a message execution takes, for example, on average, 99th percentile, how many instructions it uses, also on average, on 99th percentile. So this will give developers visibility on how the canister is performing in the real world. What is already planned is to surface the instruction counter to the canister so that the canister can query how many instructions it already executed. Another thing that's important, so this is kind of for performance, and another thing that's also important is to give developers way to get the current memory usage of the canister. I had a chat yesterday, and Motoko folks told me that it should be already possible in Motoko. So if you import this module, then you will get the heap counters, and so you can query the heap counter from your canister. And if you then additionally provide endpoint to querying that from the canister, you should be able to get the current memory usage from Motoko. But it would be nice if you had a solution that works for all languages here. And another thing that I think is very important, but I don't know any tools that can help with, are memory leaks. So a memory leak is a kind of a bug where an application or canister keeps a reference to another object that is not used. So the memory leaks happen in all languages, but I think that tooling works very well for managed languages, the ones that have garbage collector. I'm drawing here from my experience in Chrome. Previously I worked in Chrome, and I know that the memory leaks are a huge problem on the web in general, in JavaScript. But in JavaScript, it's easier in the sense that, okay, if there is a memory leak, the worst that happens, the memory usage of a tab in browser grows to some limit. And at that point, the tab is going to crash, and the user just reloads the page and continues, right? So it's not a huge deal if there's a memory leak, and of course it consumes a lot of memory and reduces performance, but it's easy to recover from it. And in our case, what happens if a canister has a memory leak and it grows to 4 gigabytes? At that point, the canister is going to get stuck, right? And developer now needs to intervene and somehow try to fix it. And so the cost of memory leak bug is much higher here. And to help with that, like ideally we have tools to help developers to find memory leaks and fix those. And there are standard tools. I'm also like drawing from JavaScript experience. Like the JavaScript has, at least the Chrome DevTools has heap snapshot generator, which allows you to get the object graph and then look for each object what other objects that are keeping this object alive. So this way you can investigate memory leaks. And another useful tool there is sampling allocation profiler. So what it does, it gives you a list of functions that allocated a lot of data, and the data was not freed later on. So that's kind of the list. It's mostly in the context of memory systems. And yeah, with that, I think I'm at the end of my talk and happy to take questions.
Awesome. Let's take a look. So one person is asking, what is the recommended strategy to handle data larger than 4 gigabytes?
So there is this stable memory, right? So I was talking in this talk mostly about WebAssembly memory, so WebAssembly instance memory, but Internet Computer also provides a stable memory. And for stable memory, we can support a larger memory because due to like technical things, the address range of WebAssembly instance, like it's limited by 32 bits, right? And for stable memory, we can use 64 bits. So this means we can support larger memory. So the strategy would be to try to keep most of your data like in stable memory and use WebAssembly memory as kind of the cache for it to enable quick access.
Cool. So next question, can't you upgrade the canister to fix a leak sometimes?
Yeah, I guess that would be the only option to, like once a leak causes the canister to go to the like memory limit and then canister is stuck. I think the only way would be to upgrade. And there we need to ensure that the code that upgrades the memory, like these hooks, like pre-upgrade and post-upgrade, they also don't use a lot of memory and don't hit the leak, like the memory limit right away. So that's, I think that upgrading would be the only way to fix it. But then I guess it's worthwhile for developers to also test it, that if they hit the memory limits, that they can upgrade safely and gracefully there.
Great. Okay, so that is the list of the questions that we have received so far. If you're listening in and if you have questions, feel free to drop it in now that we have Ulan and both Claudio on the line. Okay, so follow-up question from the person who asked the question around the recommended strategy to handle data larger than 4 gigabytes. How do we access stable memory? Is it just marking the variable as stable?
I think, I guess it's in the context of Motoko currently. Yeah, I think currently it is by marking the variable as stable. I think the Motoko team is planning to add more features to expose. Yeah, like Claudio, please go ahead. Like Claudio is from Motoko team.
Cool. So I can, so Claudio, I can give you permission to talk. Okay, so Claudio, you should be able to unmute yourself and talk now.
Okay, so at the moment, can you hear me?
Yep. Mm-hmm.
Okay, great. So at the moment, stable variables are only stored in stable memory kind of between upgrades. So they're like stored on in WASM, ordinary WASM memory during execution. And then when you schedule an upgrade, the stable variable contents gets persisted to stable memory temporarily. When the canister comes up after the upgrade, the stable memory contains those serialized stable variables, and they get deserialized into the ordinary WASM memory, and stable memory is no longer used. So we actually have like an experimental implementation that lets you use stable memory directly while the canister is executing, and also does the song and dance to avoid stable variables and stable memory clobbering each other during an upgrade. And we've actually kind of shipped it as an experimental library. We haven't documented or announced it because we're not very happy with it, because it's a very non-modular feature. So we're giving users direct access to stable memory. That means that different libraries can make different assumptions about what the stable memory is doing and can totally break their invariance. So we're reluctant to ship this, although I think a lot of users would find it useful. At the moment, we're just supporting the 32-bit stable memory API, but we could extend this work to support the 64-bit stable memory API as well. We just haven't done it yet, partially because we're worried whether this is the right solution to ship. Does that answer your question? So if you really want to try it, you can use it. There's a library that's available on the Motoko-based repo that you can use called experimental stable memory, but all bets are off that that'll actually be supported in future.
Cool, thank you, Claudio. So another question, maybe not directly related to the topic, but in the last few days, we saw some stress tests of the network. Do you have more information around that?
Yeah, indeed, like some of our colleagues are doing stress testing. It's like part of the effort, like kind of staying ahead of the curve and also finding out more performance bottlenecks. I'm hoping that once the results are there, like there will be some public announcement of that, but I don't have more information on this.
Okay, so next question. So at the moment, we cannot access stable memory in real time. What is the library called?
Claudio?
Yeah. Experimental stable memory.mo. It should be included in a latest release of DFX. So like 0.83 should actually have it in there. We just don't tell you how to use it. But we do that for a reason, because we don't know whether we should actually ship this. We've kind of shipped it on the side, and the support is there, but we might rip it out in the future. And it coexists with stable memory, with stable variables. So you can use both stable variables and stable memory at the same time. It'll kind of, it's like a small abstraction over the raw stable memory that allows us to, like, when we do an upgrade, write all the stable variables to some extra space in stable memory without affecting users' stable memory data.
Cool, thank you. All right, so those are all of the questions that have been submitted. So I can give people a little bit of time if they wanted to submit a last minute question. But in the meantime, thank you to Ulan and Claudio for answering the questions and for the very helpful presentation. Okay, I'm not seeing any more additional questions come through. So once again, thank you to the community for your amazing questions and for tuning in as always. Thank you for Ulan for preparing this information and presentation, and Claudio for the assist. And we will see you next week for a future community conversation. Bye, everyone.
Thank you. Bye.